This is Manchen Wang, and this is my lab report for Lab 4 Oscillation. I'll be introducing my lab report in the following aspects: introduction, data collection, codes, discussion, and conclusion. Here's the introduction of my lab report. The purpose of this lab is to observe and analyze the motion of an object attached to a string and moving as the string contracts and stretches. And also, using the computational model, we'll predict the motion of the object and predict the change in energy of the object as it moves. And the result of the lab is that the total energy change remains zero while the object moves on the string. So fundamental principles behind this lab are Newton's second law and energy principle. We use the Newton's second law to predict the motion of the object using force analysis, and we use the energy principle to predict and plot the energy change in the object. For my lab, I used the sample video posted to analyze, and using tracker, I obtained the position data of the moving object. Also, from pre-lecture video number 52, the following data listed were extracted for later usage in the computational model. Here are detailed position data for X versus Y from the tracker analyze. Here are codes I set for the initial conditions of the moving object. So the ball's position is indicated by this vector here, as I set the origin point at the fixed end of the spring, and the ball was initially at rest. The constant of the objects and the spring were listed here. And for gravitation, and here are general calculation of the initial energy in the object. And for the gravitational potential energy, the fixed end of the spring was about 1.15 meters from the ground, so the height of the object was calculated using the function here. Here are the codes for the calculation loop of the object. So in this case, we first update the position of the object using Newton's second law here, and then we use the energy principle to update delta K and delta UG and delta US, and finally delta E using formulas here. And also, we first stored the initial condition of the energies in a loop here. Here are graphs for the predicted and experimental object's motion. This can help us to confirm that the computational model has the same moving pattern as the experimental object. Here is the result of the computational model. On the left-hand side, we have the energy plotting graph as opposed to time. As can be seen, the delta total energy has remained the same. As in the ideal condition we assume in the computational model with no loss of energy, we have as the strings stretch in length, the spring potential energy increases. Also, the gravitational potential energy would decrease since the height of the object from the ground decreased. The kinetic energy would increase from rest and then decrease to zero again during the motion as the velocity of the object has the same change. Here is the discussion of the lab report. So our first what-if question is answered in the previous slide with the analysis of the energy plotting graph. And for the second what-if question, using the data you obtained in tracker, make two separate estimates of oscillation periods and compare the two estimates and discuss. So on the x direction, we have t equals to 1.6144 seconds, but on the y direction, we have t equals to 1.4814 seconds. So in this case here, I think the difference in cycle from x and y direction can be due to the tilted angle of the motion, and this estimation can cause a difference in the calculated spring strength if we use the if we used cycle from different directions, which can cause an ultimate error in the calculation of motion.